Okay, in this video I'd just like to review a couple of the interesting questions that came up during the MathXL optimization problems. We talked yesterday in class about number 9, and I think we ended up finishing this one out, but the big takeaway from here, of course, is that we've got this interesting objective function. The total time necessary to travel by boat and by walking on the beach is a combination of two small functions. Um, the modification of the old physics rule, distance equals rate times time, left us with time equal to distance divided by rate, and so that information was provided for us in the problem. For the second part, the more interesting component, again, we were making the argument that we needed to find a new rate for which to row the boat, such that the time would be optimized by traveling straight to the restaurant without stopping or without walking along the beach. And we kind of got hung up on this, but ultimately I think we discovered that by treating this rate as a constant, this is a constant value, not a variable, we could then differentiate in terms of x with r acting as a constant, and we would obtain a new derivative function. And this derivative function, as usual, would be solved when it's equal to 0. And so we're looking for the new r value that would make this derivative equal to 0. But, and many of you did point this out while I was struggling a little bit with it yesterday, but the r value that we're looking for requires a target x to be 12 miles, at least in my example, because we're insisting that the boat travels directly to the restaurant rather than going to some point along the shore. So since we're traveling horizontally 12 miles, we're replacing our variable x with that and then solving for our new r rate. This is the result we end up with. And a quick calculation off the screen shows that speed is about 2.91 miles per hour. So initially we could row the boat at 2 miles per hour. That was our initial rate in the water. But if we could increase our speed to approximately 2.91 miles per hour, then it would make sense for us to row directly to the restaurant. Moving forward, I don't think number 10 is too challenging. I'll zoom in on my solutions if you'd like to pause the video and see that. But I noticed that the flower garden had a constraint value to it. The area of the flower garden was 494 square meters, and additional dimensions surrounding it for this walking path were also included. What I will note with this example, though, is that when I see this problem, I start establishing my own variables. I think x and y, length times width, a times b. I just use letters that I find most useful, and I try to solve the problem before reading through the instructions on MathXL. In MathXL, they come by and try to establish which letters we should be using. So that does make it a little bit more difficult, changing letters in the middle of the problem. But personally, I think that being able to solve the equation that makes sense to you is going to be more important than just simply solving it for MathXL's case. So hopefully you can see this on your screen, but I wrote my constraints in terms of x and y, and I also included that two additional constraints for the total area a and b are x plus 4 and y plus 2. That helps me understand the problem a little bit more. And then when I wrote my objective function, which is the lowercase a times b for the full area, with the direct replacements and rewriting my constraint value inside this function, I was then able to solve for x and identify the x component that would minimize this garden's area. I'm sorry, I think it was a dimension actually. Yeah, minimize the dimension x. No, I was right. We are trying to minimize the area, and that was the x value that would minimize the combined area of the flower garden and border. So again, I'll just sit here for a second so that you can view my work. I did try this a different way as well. So if I had written it in terms of another variable, this is the math that would be put on display there. Okay, moving forward from here, I think 11 was pretty straightforward. We've seen one like that before. But number 12 got kind of interesting, only because what I feel is important information wasn't provided. We do have to draw upon some prior knowledge to help solve this. Now, with this rectangle that's built inside of a semicircle, it's kind of important to recall some things here. First off, the formula for a circle, r squared equals x squared plus y squared, that would generate a circle centered at the origin. So assume that the origin of a xy coordinate plane is located right here at the center, then the circle, the semicircle in this case, or the full circle if we had a complete window, would be represented by this equation. With a radius of 4, we would say 4 squared is equal to x squared plus y squared. And then if we had to solve for y by itself, we might write y squared equals x squared minus 16. Oops, I think I did that backwards. Start with the 16 minus x squared, and then ultimately square rooting both sides. The top half of the semicircle would be the positive square root of 16 minus x squared. Now again, this formula, if drawn on a coordinate plane, would represent this circle, and as it turns out, the height of the rectangle here is dependent upon the y position of the circle. So we do need a formula like this. In fact, when I first sat down to do this problem, this is the formula that I started with, and I used that as my constraint inside an area formula that looked like this, 2 times x times y. Because in using this formula over here on the left, x would simply be the distance from the origin to the right-hand side of the rectangle. But in order to calculate the area of the rectangle, you need the full base, which in my initial attempt required 2 times x. Now, given the suggestions by MathXL, we've got to be real careful here because they're telling us that the base of the rectangle is all of x, just 1x. And they don't really imply that we should write this function, centered at the origin. So what's important to note is that the x value here that is acting as the entire base actually only requires half of x to be placed inside the circle formula. So when I use that idea in my constraint, half of x squared plus y squared would equal r squared, and so on and so forth. That's what leaves me with a constraint function of y equals square root of 16 minus x squared over 4 instead of 16 minus x squared. And with that constraint function, I was able to rewrite my objective, which should have been x times y. We don't need 2x this time because x does represent the full base. The area x times y, when differentiated, leaves us with a formula that looks something like this. I had to be real careful here because it did require the chain rule to differentiate. But with some careful planning and preparation, we do end up with an appropriate derivative here. And my apologies, I was getting just a little bit lazy. Square root of 16 minus x squared over 4, and square root 16 of x, square root 16 minus x squared over 4. At this step, it may not be immediately clear, but I did multiply both sides by this denominator on the left. So I multiplied both sides of the equation by this denominator to make it disappear from the left. And in essence, it was the same as squaring the constraint function on the right-hand side. From there, the end result kind of presented itself in much the same way that we would anticipate. What I didn't quite anticipate, or what I didn't expect to see, was that while my solution was going to be the square root of 32 simplified to 4 times square root of 2, as I checked my answer against the answer suggested by MathXL, the format was a little bit different. Their suggested answers were of this form: some number divided by square root of 2. And while I'm not opposed to seeing radicals in the denominator, I was a bit surprised to see that was the suggested result. Fortunately, however, when I simplify the fraction, 8 over square root of 2, or 4 divided by the square root of 2, both of those numbers end up computing to the same decimal value that I obtained with my normal approach here. So I'm not too overly concerned about it. I bet MathXL has an evaluation tool that would accept this as an answer for radical 2 instead of its fractional equivalent. Same thing with the y value. 2 square root of 2, I'm sure, would suffice. You don't need to write your result as a fraction. Okay, now number 14 got really weird as I worked through that one finally. I wouldn't anticipate a question like this showing up on any test of ours in the future. It's a good question. I do like the optimization component that goes with it. It's just a very strange question to ask, very time consuming to try to understand, and definitely not worthwhile for a test of your understanding of optimization. I think the big trouble that we had here was that the constraints aren't real clear. We don't know how fast this dog swims. We don't know how fast the dog runs either. And we don't know the distance for which this dog is traveling in the water. But it's essentially the same as the boat problem from before when we were trying to row to a restaurant, except we're starting at a position on the beach. We're traveling some distance down the beach and then entering the water to retrieve this ball. So we're still going to utilize this time equals distance over rate assumption, but establishing our objective function is going to be difficult based on the unknown parameters that we're provided with. So the time function written with distance 1 and distance 2, rate 1 and rate 2. Rate 1 would be the rate at which the dog runs. Rate 2 is the rate at which the dog can swim. Those were given to us as values r and s. And then the distances traveled, well, this part of the travel along the beach is z minus y. And then this distance here along the diagonal would be the square root of x squared plus y squared, a result of the Pythagorean equation and these given constraints. And so we had to differentiate the time function based on those parameters. And just like I did in class the other day, I chose to write this as a fraction 1 over r times the numerator and 1 over s times the numerator. For me, it's a little bit easier to differentiate that way. I treat the fraction as a constant, and then I can derive with respect to, in this case, y. The instructions were to evaluate this function in terms of y. So I differentiated everything in terms of y, and then I kind of cleaned up the formula here and rewrote it as a single expression. I checked against the result in MathXL, and this is exactly what they expected to see for the derivative. Now, as we continue with our typical approach, we would want this derivative to be set equal to 0, and then solve for an appropriate value. In this case, we're trying to isolate y, so we did have to utilize some interesting algebra. I did move the 1 over r fraction to the left-hand side. And then I multiplied both sides. I'm sorry, I didn't multiply both sides, but I cross-multiplied in order to eliminate the fractions. So that's where my ry is equal to s times the square root. At this point, I squared both sides of the equation. And after squaring both sides of the equation, I distributed the s squared into the parentheses. Now I'm trying to collect all my y squareds on one side of the equation. And I utilize the y squared as a common factor. And so now I have y squared times a quantity r squared minus s squared. I could then divide both sides by r squared minus s squared. And then finally, to isolate y, square root both sides. And I'm left with the square root of s squared x squared over r squared minus s squared. And I happen to notice that this was factorable. This is a difference of 2 squares, so I went ahead and wrote that as a factor. Now I will note too that I just kind of got in the habit of performing a bunch of algebra steps here, and I wasn't looking real closely with the instructions in MathXL. I think they're trying to be helpful in providing all these sub-steps here, giving you ideas of where you should be going next. But to be honest, it was kind of difficult for me to fill in all of those components because, well, my algebraic approach differed just slightly from theirs. And I'd also like to note too that computing for y, this is actually a fine place to stop. I don't have any problem with leaving an answer this way, but for some reason MathXL's objective was to get the x in the numerator by itself and leave the square roots in the denominator, as you see here. And so in order to complete that step, it was a bit more of a challenge. So what I ended up doing was using a distribution property of exponents, recalling that the square root is nothing more than a some base to a 1/2 power. When I've got a series of multiplications like this s squared times x squared and the r minus s times r plus s, all of those terms are multiplied together. So I could technically distribute this 1/2 power to every one of these terms. And in doing so, I end up with a result that looks something like this. Sx over the product of these two squares. And then what makes this even more tricky was that in the next step, it's required that we utilize the letter s as a common factor between the two terms in these two expressions. And so that's a bit unusual to see at first because it doesn't look like there's a common factor between r and s. But, technically speaking, strictly speaking, you can divide both of these terms by s. And that's what I've done here. Now, when you divide both terms by s, you're left with this weird fraction at first, r over s minus 1, and then r over s plus 1. But again, the benefit here is that I can collect like terms. And from this grouping, I have a square root of x that can be isolated. Sorry, that's a square root of s that can be isolated. When those two terms are collected to the front, I have the square root of s times the square root of s, which is s by itself. And now, pretty handily, the s values are able to cancel with one another. They factor each other out from the numerator and the denominator. And this is what leaves us with the target that MathXL was working for us to get towards. So from here, the questions are kind of multiple choice, and they lead us along this pathway. I kind of disagree with the answer for number 8. I would go as far as to say that not only is this value of y a critical point, but I would actually indicate that this is a minimum. This is a minimum of the function t because t double prime, and this is kind of interesting. They expect us to compute the second derivative, but don't give us much lead time here. So I went back to my first derivative computation and tried the chain rule with that, chain and quotient rule for that matter, to derive the second derivative. And this is the result I came up with there. But again, back to this statement, this number 8 is a critical point of t because the second derivative is positive for all values of y. So if we have a first derivative that's equal to 0 and a second derivative that's positive, then we know we found a local minimum on the graph. For part C, we're finally given some values. The dog runs at 5 meters per second, so that's a value for R, and the dog swims at 2 meters per second. That's a value of S. So now we can establish the ratio that produces the fastest retrieving time. And this ratio represents a measurement of distances. What's the distance x and y compared to x? What ratio between this dimension and this dimension lead us to the fastest retrieval time? And as soon as they start mentioning ratio here, perhaps the trigonometric functions start creeping into our mind, and ultimately we'll utilize tangent to verify, or we could use tangent to verify the position or the angle for this dog's approach in the water. But long story short, now that we have R and S, we can make the substitutions into the formula that we established from a few moments ago and compute the ratio y to x. This problem didn't ask for it, but we can use those two ratios and a tangent function to establish the angle of approach in the water. I do realize this video is getting kind of long, so I won't actually talk through the very last example, but it too is kind of an interesting one in that we have these parameters that are somewhat difficult to follow or make our math a little bit vague. What was interesting about it, though, is that as I tried to establish my objective function and I tried to solve the objective, as they described down here, I just thought it was interesting that I made a huge mistake, and I spent a lot of time making that mistake. And I didn't know that it was a mistake until I got to the very end here. It's not that my algebra was wrong or anything, but the methods that I used, and I'll let you pause the video and pine through this if you'd like, but the methods I used to try to combine like terms and isolate x, they just ultimately didn't get me anywhere. I couldn't quite isolate x, and the trouble I was running into was this notion here, that I had a quadratic including x, a quadratic binomial including x on the right, and then a plain quadratic non-binomial on the left. It made it very difficult for me to isolate for x squared. So I went back and tried it a second time and found a much more elegant approach. Unfortunately, I don't have a description that'll help you recognize when your approach is going to work or not. There's sometimes just no knowing until you get into the algebra. Fortunately, in this approach, it was a little bit nicer. Instead of moving, I think the big difference was instead of moving this term to the right side and making it negative, I moved the other term. I moved this guy to the right side and made it negative. And in the process of making this term negative, I was able to switch the numerator. Instead of x minus d, I got d minus x, which proved helpful because in the denominator's radical, I had some terms with d minus x that helped me isolate for the variable x. So anyway, pause the video, read through this if you'd like, or you can look at the sample solution that I've posted online, and we'll reconvene on Monday and hopefully go over this with some more detail in preparation for your test middle to late next week. Thanks.